All right, welcome. Today, we're going to pull back the curtain on one of the most common and, let's be honest, frustrating parts of daily life, waiting in line. We're going to dig into the hidden math that secretly runs every single queue you've ever stood in. You've definitely been there, right? You pop into your favorite coffee shop. One day, you're in and out in like 2 minutes flat. The very next day, the same line is just crawling. It feels like an eternity. So what gives? Is it just random bad luck, or is there something more predictable going on here? Well, let's call this whole thing the coffee shop problem. And to really solve it, we're going to need a pretty powerful tool from the world of mathematics that's designed for exactly this kind of situation. And that tool, it's called queuing theory. Yeah, it's a real thing. It's basically the mathematical study of waiting, and its principles are used absolutely everywhere to make things run smoothly, from call centers trying to figure out how many people to have on staff, all the way to the web servers that deliver you content like this. So let's dive into the most fundamental model in all of queuing theory. It's called the M/M/1 queue. And I know, that name sounds super technical and intimidating, but once we break it down, you're going to see it's actually incredibly simple. Okay, so that first M stands for Markovian, which is really just a fancy word for memoryless. It's all about how people show up to the line. Think of it like raindrops hitting a window. The arrivals are totally random and unpredictable, but over time they happen at a pretty steady average rate. We call this rate lambda. You guessed it. The second M also stands for Markovian. But this time, it's describing the service. You know, how long does it take the barista to actually make each coffee? Well, that's random too. Most drinks are quick, but every now and then you get a super complicated order that slows everything down. This average service rate is called mu. In the one, this is the easy part. It just means there's one server. In our coffee shop, that's our one heroic barista, handling every single order. So M/M/1, random arrivals, random service times, and one server. See? Not so bad. Now, for this model to work, it does rely on a few key assumptions. You know, like having unlimited space for the line to form, and the system being memoryless, which just means the past doesn't affect the future. But the most important rule is one we all know and live by. First come, first served. No cutting in line. So how do we actually use this? Well, it all boils down to one single, incredibly important number. A number that tells us pretty much everything we need to know about the health of our queue. And this magic number is called traffic intensity, represented by the Greek letter rho. All it is the arrival rate, lambda, divided by the service rate, mu. Put simply, it's a direct measure of how busy the system is. This little number is the key to unlocking the entire puzzle. And I'm not exaggerating, because this one number, rho, is the only thing that stands between a nice, smooth-flowing line and complete, utter chaos. The fate of your morning coffee rests entirely on its value. And the effect of rho is, well, it's dramatic. If rho is less than 0.5, meaning the barista is less than 50% busy, the line is stable and fast, no problem. As it gets up to around 0.8 or 80% busy, you start to feel that slowdown. But here's the cliff. When rho hits 1, that means people are arriving just as fast as they can possibly be served. The system becomes unstable, and mathematically, the line just grows to infinity. It's a total breakdown. And look, this isn't just some abstract idea for coffee shops. This core principle of traffic intensity applies to countless critical systems that we all rely on every single day. Think about it. Call centers use it to figure out how many agents they need so you're not on hold forever. Web servers use it to manage traffic so websites don't just crash. Even hospital emergency rooms and fast food drive-thrus use these exact principles to manage patient flow and optimize for speed. Getting this number wrong has real, tangible consequences. But here is the final, and honestly, the most powerful insight from all of this. It's the reason our gut feeling about busyness is so often wrong. Because the relationship between how busy a system is and how long you have to wait, it isn't a straight line. It's governed by this little formula right here. The average number of people in this system, L, equals rho divided by 1 minus rho. Now, you don't have to memorize it, but just look at what happens to that bottom part, that 1 minus rho, as rho gets closer and closer to 1. And this is the big aha moment. When our barista is 50% busy, rho is 0.5. The formula predicts an average of just one person in the whole system. Totally manageable. But when the barista is 90% busy, the average number of customers jumps to 9. That's right, a 9-fold increase. that seemingly small jump in busyness has a massive, outsized impact on the line. So here is the crucial point, the main takeaway from all of this. As a system gets closer and closer to 100% capacity, wait times don't just get a little longer, they explode. They grow exponentially. And that is why a system that feels totally fine at 80% busy can feel like a complete and total disaster at 95%. It's the non-linear truth of waiting in line. So the next time you're stuck in that coffee line from hell, you'll know exactly why it feels so slow. It's all about that traffic intensity, that little number row getting dangerously close to 1. So now that you understand the math behind the madness, how would you fix it? Would you try to speed up the service, or maybe find a way to manage when people arrive? The solution, as it turns out, is all in the numbers.